massive space telescope deployed in Russia's mysterious Lake Baikal. Although the underwater neutrino telescope has not yet been completed, it has been collecting data since 2016. The Russian Baikal GVD neutrino telescope, an array of optical neutrino detectors located in the water column in the southern part of Lake Baikal, has been officially put into operation. The construction of the telescope has been going on since 2015. Physicists began collecting data on neutrinos with it in 2016. The Baikal GVD, Gigatron Volume Detector, neutrino telescope has been under construction since 2015. Since then, every year from February to April, physicists from the Institute for Nuclear Research of the Russian Academy of Sciences, together with colleagues from the Dubna Joint Institute for Nuclear Research, have been installing new clusters. The telescope itself is located at a distance of 3.6 kilometers from the coast and reaches a depth of 1,366 meters. Each cluster of the installation includes 8 garlands 525 meters long with 36 optical modules on each, recording Cherenkov radiation. The distance between the garlands is 70 meters, and between the photodetectors on the garland, 15 meters. To date, 7 clusters have been installed while the 8th has been installed in April 2022. After the installation of the 8th cluster, the effective volume of a detector should reach 0.4 cubic kilometers. Diagram of the Baikal GVD neutrino telescope. In the future, the effective volume of the telescope should be increased to a cubic kilometer. Neutrino interacts very weakly with matter. In order to detect such a single interaction, huge detectors with hundreds and thousands of tons of liquid scintillator, and hundreds of photodetectors that track weak flashes during such interactions are required. But even such neutrino instruments catch only several tens of neutrino events per year. Astrophysical neutrinos are of particular interest to physicists. These are ultra-high energy neutrinos that can be produced in active galactic nuclei. Since neutrinos do not react to magnetic fields like charged particles, they are not absorbed by interstellar dust like photons but carry information from the scene. In particular, it was neutrinos who were the first to tell scientists about the 1987 A supernova explosion, in the Magellanic Cloud, before astronomers saw an optical flare. Baikal GVD's field of view, it sees the southern sky better than the IceCube neutrino telescope. However, neutrinos are continuously born on the Sun, in the interior of the Earth, in the atmosphere, in nuclear reactors, and in order to isolate relatively rare astrophysical neutrinos from this background, really huge detectors are needed, in which huge volumes of water or ice are used as a working fluid. What advantages does Baikal GVD have over the IceCube neutrino telescope? The largest and most famous installation of this class is the IceCube neutrino telescope, an array of optical detectors frozen into the thickness of Antarctic ice, which began to be built in 2005, and in 2010 increased its volume to a cubic kilometer. The volume of IceCube is 1 cubic kilometer, and so far the installation has registered about 100 ultra-high energy neutrinos, including several with energies exceeding a peta-electron volt. Baikal GVD began to be built relatively recently, so its results are still more modest. Nevertheless, Baikal GVD has another fundamental advantage over IceCube: lower angular resolution. The fact is that ice scatters light much more strongly than water. Because of this, for most astrophysical neutrinos that IceCube recorded, the angular resolution is very high, up to 15 degrees, which means that it is impossible to accurately reconstruct the location of the source of astrophysical neutrinos from such events. In contrast, Baikal GVD is expected to have a higher angular resolution of 2 to 3 degrees, which is typical of underwater neutrino telescopes. Has the Baikal GVD neutrino telescope made any discoveries already? The Baikal GVD neutrino telescope is not yet completed, but that does not mean that it is not working. Since 2016, scientists have been collecting and processing data obtained on already installed clusters. The scientific leader of the project, a physicist from the Institute for Nuclear Research, Gregory Domagotsky, recently reported that by now scientists have seen 12 candidates with energies up to hundreds of tera-electron volts using the Baikal installation, of which about half, after verification and confirmation, may turn out to be real astrophysical neutrinos.